This is the conclusion of section 11.4 in the Briggs calculus textbook. It's calculus in polar coordinates. In this video, we're going to be talking about the arc length of a polar curve. And we've studied arc length in the past. We've seen the arc length formula if we have y equal to a function of x. Well, in this case, we're going to be looking at the arc length formula when r is equal to a function of theta. And recall that r is thought of as a radius, theta is thought of as an angle in the conventional sense that it's measured counterclockwise from the positive x-axis, just like when you've studied the unit circle in the past. So let's say we had some kind of polar equation. It could be r equals theta times e to the theta or something like that, just some sort of function of theta on the right. And the theta values will exist in a certain interval. Maybe we're going from 0 to pi halves. Well, if you do think of the unit circle, if you go from 0 to pi halves, that describes angles in a certain quadrant. Think about what quadrant that would be. 0 to pi halves, that's quadrant 1. If we wanted to find the length of this piece of the curve, then we would use the following integral with bounds 0 to pi halves. So in this example, 0 to pi halves was mentioned. So you'd have alpha equals 0, beta equals pi halves. But of course, in general, you could have any real number bounds for your theta. And so we can describe the arc length formula in general like this. If r is a function of theta, r is equal to f of theta. Theta is just going from some number alpha to some number beta. Compute the arc length in this way. And notice that it is the square root of something squared plus something else squared. So it really does relate to the Pythagorean theorem ultimately. You could say it also is similar to the arc length formula we've seen in the past if y does equal a function of x. So anyhow, in the polar setting, we have this formula, and notice that since r is equal to f of theta, in shorthand, we can think of the formula as the integral of r squared plus r prime squared. Another reminder here, which you shouldn't be making this mistake at this point in your math career, but make sure you know that the radical does not distribute. Some students might look at an expression like this and think that it simplifies to r plus r prime, but it doesn't. You can't distribute the radical across a plus sign like that. So um, we'll look at example 2 here using this idea. R is equal to 4 sine 3 theta, so that's like our f of theta. And you could graph this with your graphing calculator. Let's try to answer a two-part question. And you're just seeing part 1 at the moment. Algebraically determine the bounds for theta that describe one petal of the rose curve that appears. So if you did actually put this in your calculator, you should see a rose-looking curve, like a flower-like curve. And let's see if we can find the theta bounds for just one petal of that flower. You can find them by hand, but then confirm them with your graphing calculator. So I'm going to go ahead and pull up the shape that you would see, and then I will show you how to find that theta value by hand. And a hint here that's really helpful is that if you are at the origin, then the radius value r will be 0. I brought up Desmos.com. It's an online graphing calculator, but you can do similar things with a calculator like a TI-83 or TI-84 as long as you're in polar mode. So you could hit the mode button and change to polar. Anyhow, on Desmos.com, to type theta, you can just spell it out, Theta. So in our case, if I look back at our function, that was 4 sine, S-I-N, and then in parentheses, 3 theta. Like I said, if you just spell it out, Theta, There you go. There's our polar rose, as it's called. It looks kind of like a flower, or more like a propeller to me, but I could see that as a flower as well. And some of these things will have like five petals to the flower. This one happens to have three. Um, and let's just focus on one of these petals. Let's stay in quadrant one, just so it's easier to think about. All the x and y coordinates will be positive. So if we are at the origin, then r is certainly 0. So if you have this equation, 0 equals 4 sine 3 theta, you can, of course, divide both sides by 4. So it implies 0 is actually equal to the sine of 3 theta. You can take the arc sine of 0 even. So from this, we find that 3 theta could be equal to the arc sine of 0. That's one possibility. The arc sine of 0 is 0. So you'll see that theta equals 0 as one option. Just divide both sides by 3. And yeah, arc sine of 0 is 0. So theta equals 0 is what we get algebraically from that equation. But remember that there are other angles you can plug in here for sine to get an output of 0, like the sine of pi, for example. The sine of pi does equal 0. So let's look at what happens when 3 theta is actually equal to pi. Well, theta itself would be pi over 3, of course, solving that algebraically. All right, so theta is pi thirds. It looks like we're going from 0 to pi thirds um, in terms of this alpha and beta on the integral. Um, we would have alpha equals 0, the lower angle bound, and then beta equals pi thirds. I believe that describes one petal of the rose. Let's see if I can get that happening on Desmos. Yeah, if you type in polar equation and spelling out theta in letters, as I showed, you should get this automatically where it gives you options for bounds there. I'm typing in 0 and pi over 3. Oh yeah, by the way, pi, you can just type pi for the pi symbol. Yep, sure enough, there's one petal of the rose, 0 to pi thirds. Let's check out part 2 of this question. It asks us to find the arc length of one petal of the rose. And recall from part 1, we had found the bounds for theta, 0, and pi thirds. So the question here is to find the arc length, maybe without a calculator if it's possible. And one thing we know is we'll have the integral from 0 to pi thirds of something. If you follow the formula that we just saw earlier, it's the square root of the r function squared plus the derivative of the r function squared. Yeah, so here we're going to put in just the original function of theta that we were given. And then here in the second term, f prime of theta will go in the parentheses, and we got the power 2 on the outside for both expressions. All right, so I put in f of theta that was given in the question. R equals this thing for sine of 3 theta. And then f prime of theta is the derivative. Keep in mind the derivative of sine is cosine, and then we have the chain rule involved. Also, I just realized that I forgot to write d theta at the end, so let me do that. It's all of this integrated with respect to theta. Theta is our variable, So have that now. And I'll go ahead and see if I can do this without a calculator. So bounds 0 to pi thirds. And I'm going to simplify what's under the radical. So 4 squared is 16. Then I'll have 16 sine squared of 3 theta. Notice I'm not saying it's the sine squared of 9 theta or anything like that. We're just squaring the output, not the input. All right, then I'll carry down that plus sign that we had earlier. And 12 squared is 144. And then cos squared 3 theta we'll have. All right, and then d theta here on the outside. Okay, so if we had perhaps 16 sine squared 3 theta plus 16 cos squared 3 theta, in other words, 16 here instead of 144, then those coefficients would match up and we could factor out the 16, leaving us with the sine squared of something plus the cosine squared of the same angle, which would be 1. We are in part 2 of the question, and we saw that this integrand, what's inside the integral, doesn't really simplify, at least not in any straightforward way. Um, so let's just use the fn int feature of our calculator. So if you're using TI-83 or TI-84, start by pressing the math button, and then under the math menu, select fn int. Now, on my screen, it just says fn int. If you have a more modern version of a calculator, it might show that little squiggly line instead. Either way, we're going to now type in our function. So 16 sine squared 3 theta. So sine 3, and then instead of theta, I'm going to use x just out of convenience. If I were in polar mode, it would show theta when I press this button that says xt theta n, but ultimately it doesn't matter what we call the variable, so I'll just use x in place of theta. So 16, and we want to square it, so I could do power 2 like that, but that can be kind of confusing because you might think that the 3 is being squared, or the 3x maybe becomes 9x squared, but it doesn't work like that. So just to be really clear about it, I'll just say sine 3x times sine 3x, because after all, that's the same as sine squared of 3x. And then plus, oh, I almost forgot, we do need the square root. So at least this is opportunity to show something. If you need to go back and insert something, you don't have to like start over again. You can press the second button and then ins, insert, which is the same as the delete key, but when you're in second mode, you're going to be able to insert stuff. Notice how the blinking cursor now is like a blinking underline, so it looks a little different. And now we should be able to insert symbols. I want to put the square root symbol, so second and then a square root. So we have that, and it does add an opening parenthesis, so I'll need to remember to close that later on. All right, anyhow, after my plus sign, I've got 144 cos of 3x, or 3 theta if you prefer. Yeah, squared actually, so I'm going to do again times cos 3x. And I'm going to do one more closing parenthesis because I want to say this is all that's under the square root. When you put the square root symbol in the calculator like this, it adds an opening parenthesis. Now I just closed it off. So I still haven't closed off the parenthesis from fn int, actually. We're still going to need to type some stuff. So comma, now tell it what variable it's with respect to, x in my case. Then comma, lower bound, which is 0, comma, upper bound, pi over 3. As a reminder, the pi symbol can be accessed by using the second key and then pressing this button. It's the same as the wedge. Pi over 3, so pi divided by 3 there. Close this parenthesis. Again, that's going to actually close off the very first one that comes after fn int. And everything should be good to go here. I should be in radian mode for this question, as you can see, 0 to pi thirds. I'm going to go ahead and hit enter, and I'll double check that it is definitely radian mode. All right, when you see the little animation on the top right, the calculator's thinking. Okay, it came up with an answer, 8.9-ish. That should be right if we are in radian mode. So I'm going to press the mode key. Yes, radians. Cool. So that is roughly 8.91. All right, and that is the arc length of one petal of the rose. So if you think back to the original rose image, it had 3 petals in this example. So one option you could have if you needed the entire arc length would be just to triple this value. Well, that's it for this example. The last thing I wanted to show is on Desmos.com. Aside from typing in functions in Polar using theta spelled out theta, we can also use inequalities like saying r is less than this function will actually shade the region that's between the origin and the curve. So that just highlights that one petal of the rose if I go from 0 to pi thirds. And if I take away the original curve, you can see here that is just the one petal. So that's it. I hope you enjoyed this video.